There it is. Go. It'll go away when you write up there. Okay. Agree? Disagree?
Yes.
Agree. Okay, who can tell us how we know that's right?
You find the
Oh, okay. Who? One person can tell us. Yes.
Oh.
You take the exponents of variables.
Yeah.
In negative on this case, you just add x to the 0.
I think you're trying to tell us how to find it, but I want to know how we know that we're right.
Oh, you could take the derivative of that.
Take the derivative of that, and you get that, and you got it.
Yeah.
Okay, good. So I heard this being said around the room. What's very important to remember?
Let's see.
Why?
Because you could have so many different possibilities.
Infinite.
Yeah, any constant can go there. We need to remind ourselves it could be there. And if you remember, yeah?
Well, no, here, you keep saying what you're going to say. I have
Okay.
a question.
So if you remember, we have, you can sit down if you want to. Okay. There can be any constant there. When we take the derivative, if it's plus 5, the derivative of 5 is 0. If it's minus 7, the derivative of negative 7 is 0. So we have to remember that there is a constant there. It might be 0, it might be something else. There's also, we could say there is a particular solution or an initial condition. Those are both pretty much the same thing. So if I told you that this derivative, okay, or this antiderivative, I'm just going to put big F of x, right? I'll test you. Okay, so there's this big F of x, okay, which we use to represent the antiderivative, that function inside there, that 4x squared plus 6x squared minus 1, is that big F of x?
Little f.
Little f.
Yeah.
Okay.
Yeah.
We could just as easily say f prime, and I call the other one f. It's just a common notation to say that's little f there, and big F is the antiderivative, right, going the other way. Because the derivative is its own function, we say the antiderivative. I don't know. It's just a thing that we do in calculus. So if I told you that big F of 2 was 7, right, then I'm telling you that if you put in 2 for x, you should get 7 for y, and that means you could find out what c is, right?
Yeah.
Agree? Question?
That was about the quiz. What if we didn't put C? But we remember now.
But we promise you remember.
I'm going to take, like, on the tests, not on the quizzes, not on the homework recaps, but on the tests, I'm going to take a little bit off.
That's okay.
Why?
Because it's
wrong.
important.
It's
It is.
important at the very least.
Can we get back to me?
At the very, it's a good question. At the very least, it is on, you lose credit on the AP test if you don't put a plus.
Okay.
It is important. It's important to remember there is a plus, some constant.
Okay.
So, good. Any other questions, comments?
It doesn't really have relevance.
As long as it's not about Disney World and taking a field trip.
It's about math.
Okay.
Not super math. Do you do as an alternate test if we don't take the AP test?
No. That's just kind of like, I don't know. I see that as
Susan.
like punishment for not taking it. I don't really need to punish you for not taking it. Because I don't give you a grade in this class for taking the AP test. I know other AP teachers that I really love who do that. I love all the AP teachers. No, I love them all. You don't have to debate whether I love them. Okay, questions, comments about this problem, or what you think is very like this problem?
I have a question about this chapter. On a scale of like 1 to 5, how difficult is it going to get after this?
This is a 1.
This is a 1?
This is a 1.
What's the definition?
I guess it's going to get as hard as it's going to get, so it's going to get to a 5?
No.
Like,
That wasn't
Out of 10.
No, like 5 was like when we were doing like super imaginary numbers and like trigonometric functions. We had the whole like cheat sheet of nodes that was super hard to figure out.
Finding antiderivatives, It'll be. I can't remember if it's this chapter or chapter.
So it's like triple antiderivatives.
Are we gonna wanna kill ourselves? Are we gonna cry ourselves to sleep at night?
Are we just gonna be like, my husband confused or like sitting there at night crying because we can't figure it out?
This is gonna break the scale.
Logan only to give it back.
What?
If you borrow it, you have to give it back.
It's hard for me to say. Let's see. Let me think back to my calculus days. Was it one of the hardest things I ever did?
Oh God.
So that means it's at least hard. Why wouldn't it be hard?
Well, I mean, it's not gonna be easy, but I mean, it's hard compared to some of the
I
stuff we're
think
doing.
we'll find out
It's all-
eventually, and whether or not we
Probably.
like it.
No, I don't think we'll ever find out, Gavin.
I think the funny thing is hard anyway.
This is true.
Everything's
Okay. Right? This is stuff that takes up time and. No, you're blocking everybody's view.
What if I stand over here? Stand right here.
That's my spot.
You're standing over there then.
Please. Okay, so yeah. It's gonna be challenging, but if you stay with me and something I've been telling you since our very first year together, don't try to avoid the work. Just stick with me and learn the concepts. Don't try to learn the shortcuts and the tricks.
So don't be.
You
Yes.
told us that last chapter was gonna be hard, so I was expecting it, so it wasn't as like shocking when it was.
Let's see. Yeah, I mean, I wouldn't give you the same warning about this one as I did last chapter. I guess. It doesn't seem to be, for those who are really tuned in and paying attention, some of this is review, like stuff we're going to do today's review, part of it, like the first half. Let's move on to the second one, and let you guys go ahead and tackle it.
I was unsure.
Now,
Break it in pieces.
I'm continuing on now because either you got it or you're really close to getting it and you're on the right track. Okay, now keep it. My advice to somebody who's never taken an antiderivative like this before. What's that again? What is your advice?
Break it apart.
Break it apart.
So they're all individual.
So they're all individual fractions?
Feasible.
Nice. Okay. Let me give you the reason why. This is just like middle, right? We're in the middle. The reason why is because we don't know how to take very many antiderivatives. We can take the antiderivatives of what kinds of functions? I'm asking you.
Exponential.
Exponential means x is in the exponent.
Ones with power.
Ones with power, so x has a power.
Yeah.
Okay, so polynomials, power functions, not exponential functions with power functions. It sounds the same, but it's not. Okay, so we can do that, but we can't do the quotient rule. There's no quotient rule. There's very little that we can do. We can do the reverse of the power rule, right? Where the power rule for derivatives is break down the power and multiply and take one away. So we're going to bring the power up one and then divide by that power. Okay, and then we could do some trig functions. It's like maybe four kinds of antiderivatives. If you remember, for sine, cosine, and maybe two other, like secant tangent and secant squared are derivatives of some functions, right? Yeah. So, and then power functions. We just don't have a lot of know-how yet. So if we break it down into a polynomial or a bunch of power functions, we can do this. So x squared over x to the fourth becomes
Next to the negative.
2, that's not what I meant to write down, plus, there you go, plus what? 2,
X to the negative.
Or 3. Yeah.
3, 1 minus 4, minus
3
x
to the negative 4.
to the negative 4, we got the dx, it's very important. This is going to make a lot more sense today, Okay, this dx thing. Okay.
Uh,
Oh, we don't do that simple anymore because we're about to take the antiderivative and what is it? What is the antiderivative?
Negative
Just the
x.
antiderivative of this.
Negative x is negative third minus.
Whoa, just this one.
X to the negative.
Just
Negative
negative x
x
to
to
the,
the
just
negative one.
negative x to the negative 1?
Yep.
Let's just check ourselves as we move along, okay? Negative 1 times negative is positive, that's good, positive 1. Subtract 1, negative 2, good, let's move on, right?
Yay!
Minus what?
X to the negative second.
X to the negative second, negative x to the negative, let's just double check. Negative 2 times negative is 2, positive 2. We'll subtract 1, we get negative 3. Excellent, now we move on.
Plus x to the negative third.
Plus x to the negative third. Bring down the 3 times negative, or the negative 3 times positive, negative 3, great. Subtract 1 from the power, we get negative 4.
Plus c.
Plus c, very important to put plus c.
Yeah, that C really gets me.
Maybe write it flat. That's bad. Question?
So like on the AP test, do we have to put those, since they have negative x one, so those have to be in the denominator or not?
Here's the secret about the AP test. If your answer can simply be simplified or rewritten, and it's equivalent to the correct answer, like that is the official answer, then it's right. So that can be a good and a bad thing. You have to be able to just simplify the answer down to the official answer. But if you have to, if there's more than simplification that has to be done, then it's not correct. Okay. So this would be correct. This would be the same as having.
Negative 1 over x minus 1 over x squared plus 1.
Yeah, or even finding a common denominator and adding them all together. That's another option that you could take. So any of those options would be the same. But once they have to start like substituting numbers in for x, or like there's certain things that count, certain things that will be counted wrong. But this would be correct. This would be fine. And for me, this is fine because this is the same thing. Even if I write it as Aaron said, or if I find a kind of common denominator and add all these fractions together, it's all the same. Right? It gives me the exact same value if I plug in x. And the important thing is that you could do it. You could simplify it. If you have difficulty simplifying it, start practicing simplifying it. Because sometimes you just need to be able to do that. So for one, the thing that comes up the most is if you have a multiple choice answer, and they have something different from what you have, and your answer looks like none of those answers, you should try and simplify it down to what they have. So if you can't do it, you should start doing it so that you can simplify it. And do things. Anyways, those are a couple of examples. Questions? Other questions from the homework? I heard at least one.
I couldn't figure out how to put it on 56.
46.
Yeah, all those
Yeah.
graph things.
The graph one.
Just that one.
Yeah, I got all of them.
Oh, let's see. Insert page after. Okay. 46.
These I know.
So this is where they give us a graph of f prime. We're supposed to draw f. We've done this before, but that's not to say that it's just easy. Okay, so this is f prime. Let's just do f in another color, the blue. All right. So what does f prime tell us about f? Its slope. Okay. So what is the slope of f here? 0.
Close to 0.
Close to 0. So what does that mean about the original function? What's the only thing we really know about the original function? It's supposed to be. Because I need to. I think I need to draw this graph a little better.
Horizontal asymptote, which.
Wait, hold on now.
Sorry, my bad. No.
Horizontal asymptote, which means that there's gotta be a constant in there.
Red. I really need to be more accurate. Okay. So the value of the derivative right now is 0 because it's close to the x-axis, right? If I were to plug in x Over here I get a y of like 1/2 or 1/4. Something small, right? So it has this tiny, tiny slope. What does the zero slope look like? Horizontal, okay? So over here we've got this horizontal slope. Now, think about this. This is where this plus c comes in, okay? I can have a flat slope here. I can also have a flat slope here. I can have a flat slope down here, a flat slope down here. It doesn't tell me where the original function is. It just tells me that the slope is
Flat.
0 or close to 0. Getting closer and closer to 0. So you just have to pick. I'll pick here. Okay? Let's look right. It looks like there's this asymptote right here, like
Yes.
dividing line. So what's up with the slope here? It's a big, big slope, right? What's a big slope look like? Closely approaching vertical, right? So actually, original function, and these are smaller slopes, right? A slope of like maybe 1 right here, because the y value is 1. There's a slope of 1 there, so we need to have a slope of right up 1 and over 1 at that point, and then here we need to have these big slopes. This is very, very slanty. Okay. The thing that can be misleading here is that it almost looks like the slopes of f prime match up with the slopes of f, which is not the case, right? The y value of f prime tells us the slope of f. Okay, so here we go through a slope of 1. Why? Because it says a y value of 1, and big, big values, right, going towards infinity. So our slopes are getting bigger, closer and closer to being vertical. Okay. Let's see. What kind of slopes are we seeing here?
That's getting closer to 0.
Closer to 0, but what kinds of slopes are they?
Oh, 0.
Horizontal.
Are they positive or negative slopes?
They go to negative.
You're looking at the slope of f prime. Oh, what about f prime tells us the slope of the original function? The y value. What kind of y value is positive? So the slope should be so almost 0, but still positive, right? So like this, right? Slightly up and to the right. Okay. What about the slopes here? The y value of it is very big.
Yeah.
Big slopes, big positive slopes.
Yeah.
Steep and from bottom left to top right, rising. Okay. So very similar to this, only, sort of reversed. Okay. And then we have maybe a slope of 1 here as well. So a slope. This looks believable, like you can pass through there. So very steep, and then a 1, and then a 0, but all positive slopes. Okay. In reality, this could be down here. It could be up here. Like this tells me absolutely nothing about where this other part of the function is. Right? What is that plus c? Don't know. It only tells me the slopes. It does not tell me the y value of the original function. Okay? So whether I have these two parts like this, which is kind of normal and horizontal, asymptote, vertical asymptote, a hyperbola, right? Or it could be like this. It could be weird. Maybe probably not a slant asymptote. Probably has a horizontal asymptote. Okay. If I put it like this, I could move this whole blue function up and down too. Because I don't know what this plus c is. It might be plus 5, it might be plus 0, it might be minus 12. So this blue part could be up and down wherever I want because all the slopes still match up. Okay. And I also heard 49. Right? Or am I wrong? Actually, I should. I think it was already. Here's 49. Let me capture that. Can someone explain what the slope field is, what it means?
So it shows the slope at any given x point for a function.
Yeah. There's some function out there, let's call it y, okay? Well, what they're telling us about y is that this is, well, how is this related to y? It's the derivative, and what does the derivative tell us about the original function? The slope. So, we go in here, we just draw the slopes of the function because we know the value of the slope, because the derivative tells us the value of the slope, right? So when we come to say 3, comma 3, okay, that's a point. This is 3, comma 3. X is 3, y is 3. Right? So to find the value of the slope, I plug it in here. I find that dy dx, I could say of 3, and x is the only thing that matters here because there's no y value there that tells me what the slope should be. So 1/2 times 3 minus 1, that's 3 halves minus 2 halves in the common denominator, so 1/2. So that's not the y value at this point, but the value of the slope. So we go, right, kind of aim ourselves at up 1 and over 3. So up 1 and over 1, 2. This would be about 3. And aim at this point, right? 1 up 1 over 3. That's how we get this little dash right there. It's just the value of the slope of the original function. Just gonna erase. So it says draw 2 possible solutions, right? The solution to this differential equation is another function. Okay? Another function that has this as its derivative. Okay? So if it has this as its derivative, it has all these slopes. So let's say that it goes through here, then it needs to have this slope, and then you can see how it's going up. Like, it doesn't have to go through these slants, but it does need to match the slope of them. And like this. Okay? That's kind of like a parabola, or maybe some even degree polynomial. It says including when it goes through the given point. There's the given point, so we'll go through here and we see how we need to have these slopes. It needs to come down, flatten out, go through here like this, just get steeper as it goes that way. Okay. So this point is 4, comma 2. So it needs to go through that. Right? So any function that has this as its derivative, when you take the derivative of it, needs to come out to be this. So what function could we have that, this will be y, what function will have this as its derivative? One fourth x squared minus 1x plus c. When we put a point here, we make it go through that point, we're saying c is a known. Right? We just need to find it. How do we find that c? What? This graph goes through this point.
You plug in those points into that thing.
Which points? What points? This is one point.
You put,
Put this x in and you should get this y out.
yeah.
Okay? Should get 2 when you go 1/4 times 4 squared minus 4 plus whatever c is. Okay, so this will be 16 divided by 4. That'll be 4 minus 4, which is 0. So c will be 2. So we know that y, with this particular solution right here, is what we call a particular solution or an initial condition. Y is equal to 1/2 x, or sorry, 1/4 x squared minus x plus 2. C is 2. C is 2.
Mhm.
2, and we know
Okay.
what's the particular.
So is C always going to be the y?
Is C always going to be this thing?
Yes.
No, it only happened that way because when we plugged in 4, this happened to come out to be 0.
Oh, okay.
This comes out to be 1, and we just subtract 1 on both sides, C would be 1. You just want it to work out nicely for us.
Oh, they're so kind.
Yeah.
They're not actually. They give us small slope that just can't be easy.
Guess they could start it off really hard so you don't even understand what you're looking at.
That'd be good.
Okay, let's talk about this as we exit this section and get into the other one. So, what does this thing, this symbol mean to you?
The derivative of,
Find the antiderivative, right? A function that has this as the derivative. Simple enough. Okay, now this has a name that we haven't really talked about, but hey, we can throw it in now, right? You didn't need to know it to do the work. So now we're going to call it by its official name. Okay, it's called the indefinite. Okay, just notice we haven't plugged any numbers in there. We're just getting general, some other function, not actual values. Okay, so the indefinite integral. So we've done a lot of differential calculus, derivative, and now we are into integral calculus, finding indefinite and later definite integrals. Right now it's called the indefinite integral. Okay? This is the vocab you're going to want to know. You're going to be asked for the indefinite integral. It just means the antiderivative, really, for all intents and purposes. Okay, you may not know what this is called. This thing right here that you're taking the antiderivative of is called the integrand.
That's not bad this morning.
Yeah?
Yeah.
Nice.
Just working on some.
These are the things that slow us down and that really pressure our schedule. What does this tell us? What does this tell us?
But you're looking at respect to A.
That, yeah, kind of backwards of what you said, that the derivative was taken with respect.
Oh, yeah.
It's a function of x, is all it's saying. So the derivative was taken. And this is what we got. This is what we got when we took the derivative. It was taken with respect to x. That's what it's telling us. I would say maybe this is the most important thing to have just on the forefront of your mind. Indefinite integral. Antiderivative, same thing. Okay. Not this section, but the next section will know what a definite integral is. All right. Going forward, what I want you to do right now is that. Okay. If you don't remember, you got at least two other brilliant minds in your group.
Do you remember what that thing is?
So have a book if you need. Okay?
Yeah, is that X over three?
That's x over 3. That's 3 times x over 3 squared times 1/3. Just practice with summation notation. That's all it is. Okay? It's important to be able to do, though. This is summation notation. That's a review, and you all seem to, eventually crank over those rusty summation notation brains of yours. Okay, and you remember the summation notation just means we're going to find a sum. Okay, how do we find that sum? We plug in this 1, we plug in 2, then we plug in 3, and we stop because 3 is it. So we move up by integers, right? 1, then 2, then 3, then we don't go 1.5 or anything like that. So you just plug in 1, so we get first term. Oh, this is weird. Yeah, first term is 3 times 1/3 squared times 1/3. Okay, which makes me wonder about your ninths. No, it doesn't. Okay, plus 3 times 2/3 squared times 1/3 plus 3 times 3/3 squared times 1/3. Okay. So let's see. We got 3 times 1/3. That's easy. That's just 1. 1/3 squared is 1/9. Plus again, that's just 1. That's convenient. 2/3 squared is 4/9. Plus that's just a 1. 1 squared is 1, but we want it to have a common denominator, so 9/9. So we have 14/9.
Shut up, Tyler.
Okay.
You can't even have to take things into.
All right. Good. Let's try a different one. Hopefully a little more challenging.
Shut up, Tyler.
Okay, so quickly, all we're gonna do here is plug in 1 and 2, 3, 4, and 5. Have 5 terms then to add up. We're also gonna see how we can shorten this up a little bit in summation formulas. Okay. So for 1, let's use 1 right away. Notice for each of these terms, these 3 terms, that they all have common factors of 3 times 1/3, right?
Yeah.
So from the beginning, we could have taken those factors out. Like every one of these is going to have a 3 times a 1/3. So we can take 3 out, a 1/3 out, and then only deal with the part that actually varies. Okay? Part that actually varies. And then we would have had 3 times 1/3. That kind of unfortunately worked out to 1. Times 1/3 squared plus 2/3 squared plus 3/3 squared. You can factor it out here, or you can factor it out at the beginning. So here we have a 4 and a 1/5. Every term that we write down with 1, 2, 3, 4, 5 plugged in is going to have a factor of 4 and a factor of 1/5. So we can just take the 4/5 out of all the terms, then add up the terms that actually change as we plug in these different variables. Okay. Hey, you know what? We can do that a little bit more. We could actually just cube this out. 4/5 I equals 1 to 5. So 2/5 cubed is going to be 8 over 125 x cubed, if we just cube this out. So then we have a common factor of 8 over 125, so we can bring that out here. So we have 4 over 625, or sorry, 32 over 625 times this sum. Right? I didn't expect you to remember that, but I'm just showing you how to make that a lot easier. Now it's only the variable that changes with each term. All the other stuff is the same. So we might as well take it out and multiply it through at the very end when you find the sum of the stuff that actually changes. Does that make sense? Okay, so we have these summation formulas, summation notation formulas. Okay, so if from the first term to the 5th term, I want to find the sum of the first 5 cube numbers, okay, I do it like this. This is 32 over 625. 625 times this sum. Well, if we look in our books at page 260, you can see number 4 there is for the cubes, right? If you have just a term that's cubed and you're just going to plug in 1 cube, 2 cubes, 3 cubes, 4 cubes, 5 cubes, no need to do all that. There's a formula here. It says we can just take n, okay, n is 5, right? 5 squared times 5 plus 1 squared over 4. Okay? If we're trying to add up the cubes, we just take this guy right here, as long as it's from 1 to 5, not from 0 to 5, not from 2 to 5, but from 1 to 5. We can take 5 squared, 5 plus 1 squared, divide by 4. That's going to find this sum. 32 over 625 times, let's see, you got 125 times, or sorry, 25 times 36 over 4, let's see, 25 times 325. What?
The whole thing is
325?
2.
225 over 1. 225, 625, they got a common factor of 5. 25. 25. This is 5. Is it 5? No. It's 25. Yeah.
Yeah, 9.
No, it's not.
No.
25 times 25.
It's
No, it's divided.
7? Is it 7?
No, it's not.
You're divided by 25.
How you feeling?
Did you say it's 9?
right? It's
25.
Yeah, now it's
25. And then the other one is
82.
So we need to work.
I am.
Oh, that, and this one is?
8.
8.
Yeah.
Okay, that's good.
Okay, so 32 times 8 is
32 times 8? 256.
256 over 25.
No.
256 over 25.
Me too. I
This isn't good.
Huh?
And we even did it the long way.
Yeah.
We did it wrong.
Oh, wait, what's?
288 over 25.
225 divided by 25 is 9, not 8.
288 over.
So we need to multiply 32 by 9.
9.
There we go.
Who lied to us?
Okay.
So we did do it right?
I thought I was crazy. Yeah, we
Sounds
did.
like it.
Nice.
I keep.
Somebody lied.
Yes.
Is it like the n squared times n plus 1 squared over n minus 1 always the formula?
It should be over n minus 1. It should be over 4.
Always over 4?
Yeah. Oh, I see why you thought it. Yeah, yeah. Always 4. If you look on page 260, you can find
I
this.
can't remember. I don't know how to from last year.
Oh, it's okay. Okay. If we look at
Summation languages, I like it because it's super long.
here we go, right there. Here are the formulas. Guys, come on. Here are the formulas right here. This is for cubed. If you're adding up a bunch of things that are cubed, the first, just not cubed, just the first power, the first n squares, those are the formulas.
So I have a question with 2 and 3. When it's saying when it's saying I equals n plus 1 over 2 for the second summation formula.
This one, this one?
Yeah.
What about it?
So when it's saying I, is it gonna say it'll show I in the problem, or it'll?
No, it has to just be I. Or
Okay.
X, but for the I.
Okay.
You have to use those other things like we can separate them out into separate sums. We can take out constant multiples. All that
Okay.
stuff. It's definitely, we're gonna get plenty of practice of that. But to get there, let's move on to the next concept. Or really, the next question. Okay. So the first question in calculus was, how do we find the slope of a tangent line? So now the second question of calculus, that we build a whole lot off of, is for a curve, what is, say, from here to here, what's the area under this curve?
Oh my god. I was hard.
Okay.
Yeah, because then we did it like
There
yeah,
was
we did it
that's
like
a
rectangles.
Yeah, but there's an infinite amount of
So,
rectangles.
for example, let's use this function.
Summation formulas find the area.
From 0 to 1, this is negative x squared plus x. So from 0 to 1, let's find the area under the curve. Okay? So it sounds like you're remembering from last year we used rectangles, right?
Yeah.
And then we did what with those rectangles?
Use the
Add the
summation
area.
formula.
Add them up, and then to be better and better and better, use the rectangles? Okay, so for those of you who don't remember, which is fine, let's start out with 3 rectangles. Okay, we'll make it easy on ourselves. We'll make them equal width, and here's what we'll do. We'll split this into 3 sub-intervals. This is an interval from 0 to 1. We'll do it into 3 sub-intervals. So this will be 1/3, 2/3, and 1. Okay? And we'll build a rectangle where the top of the rectangle is decided by where the right side would be the function. Okay, and this one is actually going to be the same height because it's right across from there, right? It's this right side that decides how high the rectangle is. How high is this rectangle? There's no rectangle really because the right side touches the x-axis.
Which would make sense because there's added area on the right one.
Because what?
Because there's added area on the left one that it kind of accounts for that.
Yeah, maybe it kind of balances that out a little bit. Okay. Well, what are we really doing? We're adding up three things. Okay. Well, how do we decide where, like, what we plug in, or what the height of the rectangle is going to be?
By x minus, well, it's like, we can choose everything.
Now you plug the x into the function, right? So you take this 1/3, you plug it in there, right? You're gonna plug it right in there. You're gonna plug the 2/3 right in there, okay? So we're really gonna take negative I over 3, so that we maybe have 1/3, 2/3, and then 1, right? Agreed?
Oh, look, we plug in 1, 2, and 3, like that.
Yeah. 1, 2, 3.
I is basically x.
But we put it over 3 because in summation notation we're going to plug in 1, then 2, then 3.
Because
but what we
that's
want to do is add up all these rectangles which have an x of 1/3, 2/3, and 1.
Okay.
Okay? We're going to formulaize this a little bit. So we'll take that and we'll square it. Right? We'll square it plus I over 3 first. Okay. Well, what does this represent?
That represents
The
rectangle.
What about the rectangle?
oh, no, that represents where you're putting x to make the rectangles at, right?
It represents just the height of the rectangle. Right? Because we're going to plug in 1 here. What's that going to do? That's going to do negative 1/3 squared plus 1/3. Well, that's just like plugging 1/3 into this function. And what happens when you plug 1/3 into the function? You find the y value for 1/3.
Okay.
That's just the height, right? If we want to find the area of a rectangle, what do we need? Height times
Wait,
width.
You know,
Yeah. How wide is this rectangle going to be?
1/3.
What about this one?
1/3.
What about this one?
1/3.
Oh, so that's the convenient thing about making them equal width is we just get to say, well, we'll multiply this, the height, times 1/3, the width.
So what was that by 1/3? Okay.
Okay, we could plug in 1 and 2 and 3 into this and make 3 different terms and add them all together, or we can use the summation formulas. Question?
So say instead of like instead of the 0, 1/3, 2/3, and 1, say we had 0, 1, 2, 3, then the width would be 1 over 1, basically.
0, 1, 2, 3.
Or no, like from how we have that, instead of the 1/3, that's a 1, instead of the 2/3, that's a 2, and then.
So
the
this
1.
happened to be 3 here?
Yeah, so it would be.
Then yeah, the width
1.
would be 1. Yeah.
Okay.
Okay. So let's do this one real quick. Well, we got this constant multiple of 1/3, so we'll pull this 1/3 out here. Now this big sum here, we could really view as the sum of all of these little terms plus all the sums of these little, we could separate them out, right? Because if we were to plug in 1, 2, and 3, we would just have this with 1 in it, plus this with 1 in it, this with 2 in it, plus this with 2 in it, this with 3 in it, plus this with 3 in it, right? We could group all these terms together, add them up, we could group all these terms together and add them all up. Or what I'm saying here is, we have a rule that says if we have a sum of sums, we can just have 2 separate sums. This term, plus we can use summation notation, and this one. We're trying to ultimately break this all down so that we can use the summation formulas, right? It might not seem that necessary when we only have 3, 1, 2, 3, but when we have 5 and 20 and infinity, then yeah, we're going to want to do that. This is 1/3 times let's square this, okay? Actually, we can put a negative out here. It's got a multiple of -1. Negative right there. We'll square this out. We got I squared over 9. This one we could pull out a 1/3. Equals 1/3 of I. And we'll pull out the 1/9, so we got -1/9 out in front here. Squared. So this has a formula we can use for it. This has a formula we can use for it. And it's much easier. So -1/9 times, okay? We'll just use the formula from 1 to n of I squared. That's on page 260. That's n. What's n in this case? 3 is n. 3 is the last term. So we go out to the third one. So we put 3 times 3 plus 1 times
2 times 3 plus
times 3 plus 1
over 6.
6 plus this one, 1/3. This formula is n times n plus 1 over 2. 3 times 3 plus 1 over 2. And this 1/3 is way out there front. Okay, and this might look messy, but
Yeah, it does.
if it's helping you not have to add up 20 terms, it's certainly a lot easier than adding up 20 terms. So -1/9 times, let's see, let's cancel this 6 with this 3, this becomes a 2. Right. This is really a 4, right? So 4 cancels with 2, this becomes a 2. So we just have, this is all over 1, so we just have 2 times 7. This is 14. That's 1/3 times, let's see. This is a 4, so 4 can cancel with 2. This would be a 2, so this would be 6. So it would be 1/3 times 6. Uh, 9 plus 6 divided by 3 is 2. So 1/3 times, we get -14/9 plus 18/9, so we got 4/9. So we got 4 over 27. What do we find here? What is this? Of?
Area of underneath side.
What?
Yeah.
Of what?
It's the area of the underneath side of the function.
It's the area of the rectangle.
It's the area of these three
So it's the
rectangles, right? This is a rectangle with no area. Well, what are we going to do to make this better? More rectangles, and therefore thinner rectangles. And the more rectangles we use, the smaller they get. And this this too much here and this too little here gets to be less and less and less and less and less. Right? Agreed? Okay.
I got a question.
Yeah.
Can you do them with hand rectangles, like in that? Whatever number, no, I meant like, I'm trying to think what it looks like again.
What it would look like to have 10?
Oh wait, never mind, I think I remembered how it worked.
Well, if it's hard to visualize, let's just go, I don't know, undo all that. Let's maybe move down here, we'll see what it looks like with 10 rectangles.
Because you would just stop at the rectangle before it, right?
Before what?
Like the rectangle that you make before any other ones, you would stop before you go past it. Which that's what I was confused about, and I thought they all like hit the y-axis, and I was wondering how that would go to the right area. But I remember now.
Let's go ahead and graph it real quick. This is 1, x is 1, x is 0. So it's nice to draw, we're going to have 5 on that side and 5 on this side, so it's kind of nice to draw. And we'll try to split this up into 5 equal So intervals here. Okay, so if we always use the right side, which is really convenient, we'll have a rectangle like this, and this one like this, and the right side of this rectangle will be right there, and the right side of this one will be right there, and this one there. This one right there. This is one here. Go up to there, go over, up to there, over, there, over, and this one no height because it's right there. The right side of it is all the way down on the x-axis. Okay. So we can do this with 10 rectangles, or 20, or 1 million, or however many. And the more we use, you can see, the less we're off by. Right? We're off by a little sliver there, and like too much and too little there, too much of a sliver there. That's almost the same as that one. Not quite. Right? It's starting to kind of balance itself out. And if we go to infinity rectangles.
You get it.
Right. So let's get there, but first we need to write something that we can let go to infinity. Right? What number in this concept are we going to let go to infinity?
3.
What number?
Number of rectangles.
The number of rectangles.
Oh.
Okay. Number of rectangles.
So it'd be
N. N. Like, in this expression, what would be changing and what would be staying the same? Because it's going to be very similar. Right? We're using the same function. Right? So what's going to be changing? What's going to be staying the same?
I will say the same.
I starts at 1.
So you're talking about yourself.
Right?
I will stay the same.
I will never change.
Okay, so let's say that we're using 10 rectangles.
Yeah.
Right? So what's going to change about this?
3.
All the threes?
And
On the
You think N, this will be 10?
Yeah.
What else?
with,
Will this be 10?
Yeah.
This will be 10?
The width will change.
This will be 10? This will be 10 because each of them are going to be 1/10 wide.
Yeah.
Okay? Well, let's try and make a process by which we could apply this to any function. Not just this function, but any function. Okay? Alright. So we'll just generalize it for any function, f of x. We'll make it from A to B, and we want to find the area underneath the curve from A to B, using lots and lots of rectangles. We're going to we're going to add up the areas of a bunch of rectangles. We're going to sum up a bunch of things, right? We're going to sum up from the first rectangle, the area of the first rectangle, to which rectangle? The nth rectangle. And then we'll let n change for any number of rectangles that we want. Okay? The nth rectangle. Okay, well, we know that we need, for the area of a rectangle, 2 things. What 2 things do we need? Height
and the width.
and the width.
Is this going back f of x plus h?
No, not exactly, but sort of. How do we find the height of each rectangle? Like, we're going to go to some, let's say, right here. Okay? Let's imagine that this is an example rectangle, right? A really skinny one. And let's say we're going to use the right side of it. So we'll call it x sub I, because it's the ith rectangle, right?
Yeah.
Maybe the first one, second one. Maybe this is like the
800.
800, yes. The 800th rectangle. And if you think about it, I is, it could be I plus 1, I minus 1, because sometimes we have to adjust those things. But really, x sub I is appropriate because the ith rectangle should have the ith x value, right?
W is constant, right? Because
If we let them, be the same width, then width would be constant,
yeah.
right?
And then for height, it would be what you plug in for the x value on the right side,
Yep.
which would be it would just be like, every single time it'd be like how far it is from that X to B. And then you'd subtract it, that distance from the total distance from A to B, and then you'd get the X point.
Sort of. Let's walk through it real step by step here.
Or gonna
Okay.
be
So let's say this is an example rectangle. We get to this example rectangle. We want to find the height of the rectangle. How do we find the height of the rectangle?
Plug in that X value.
Plug in this x value. So we could write f of x sub I, right? But let's just say for now we're going to go back. This is too general, right? We need to be a little more specific. Let's go to the width. What's the width of this rectangle going to be?
Really
Small.
For all the rectangles, how could you calculate it for 10 rectangles?
Divide by.
When
Divide by 10, divide what by 10?
A to B.
8 of the difference from A to B. So how do you find the distance from A to B?
Divided by.
A to B, right? Yeah, but how do
A
you
minus
And
B.
A minus B?
B
minus
minus
A,
A,
because we're going to take the right
B
side
minus
minus the
A.
left side.
B minus A divided
B
by.
minus A over N, right? 10 or 12 or whatever. Whatever the number of rectangles is. Okay?
Yeah, I remember
Right. Let's take a step back so that I can explain something to you real quick. That's correct. Technically, what we call this is delta x, f of x sub I, times delta x, right? The change in x. How much you're going to move over by a change in x. Okay? But then when we call it a really small change in x, we call it a dx. Okay? You see how we have a function times dx and how we're taking antiderivatives? And we have a function times a dx comes from here. Okay? It has its roots in that. We'll get to it soon enough. So what is delta x? Delta x, here let's write that and then we'll just rewrite it more specifically. Let's do it that way. So I equals from the first rectangle to the nth rectangle. We've got the width. We know that they're going to take the distance between B and A and divide by the number of rectangles. It's going to give us the width of any rectangle because we're going to let it be a constant because that's just... Okay, so we know that we want to find the height of this rectangle right there. We're going to plug in x of I into f of x. But just like we took delta x and we made that width a constant by taking b minus a over n, definite, we can plug all that stuff in. How are we going to find where that is? Where is that x of I?
It's B minus
B minus I.
b minus i?
B minus X.
B minus x of I. Well, x of I is an x value right there. B is this x. So b minus x of I would just give me this distance.
What are we trying to find?
We're trying to find where is this? How can I write this in terms of like A and B and x and n?
Is this where the H comes into play?
Never an
Let's say it this way. Okay? Let's say with the first rectangle. First rectangle. Remember, we're going to use the right side. We're going to use A? No, we're going to use the right side. How far away is the right side from A?
I.
I?
And
And B minus A over N.
B minus A over N away, right? The width of one rectangle, right?
Oh.
How far is the right side of the second rectangle?
2 times B minus A over N.
And the third one?
3. So X times B minus A
N
over N.
times
N?
N.
I.
I times B minus A over N. That's I is the number of the rectangle you're on, the first, the second, the third, the fourth.
Okay.
B minus A over N is how wide that movement is, right? The delta x. Okay? So we're going to move over from A. We're going to start at A. We're going to move over. We're going to move to the right. We're going to move a plus. We're going to move over a width of a rectangle for every rectangle. We're at, right? The second, the third, the fourth, the fifth. We're going to move over this many widths from A. Yeah? Does that make sense? It's real crucial here. Does it make sense or does it not make sense?
Yeah.
Pretty much right now it makes sense.
This is the formula last year.
Yeah, it's the same one.
So now you're just explaining.
Relearning.
I explained it last time.
Did you really?
Yeah.
It's okay though. That's why we're going over it again. So this is the height of a rectangle. This is the width of a rectangle. Okay. And this, you know, this will give me the height of any particular rectangle. The 5th one, the 70th one, the 856th one. I just plug that 856 in there. And I multiply it by, well, if there's 856 rectangles, this rectangle is going to be really thin because I'm going to take this distance and divide it by 800, well, however many n is. So we get to the 856 rectangle, but there's 1,000 rectangles in all. Right? So we're taking that distance between B and A and dividing it by 1,000, which is really small. Take 856 really small things and add, really haven't gone
So
all that far.
N is the total number of rectangles there
Mhm.
are, and I is the one that's over.
Let's write that down. N, total number of rectangles. I, number of the, let's say like the current rectangle.
Homework. It's fine, it's past 5 minutes. But it's past 5.
I'll write the homework up, and we're gonna not lose our minds. It's gonna be the opposite of what usually happens. And we're going to work out an example together.
This guy came into Subway today and screamed at me because he wanted his honey mustard and chipotle sauce not touching each other on his sandwich. And I was like, I'm gonna fold your sandwich and they're all gonna get mashed together and go into your mouth and into your stomach. I don't think I wanted that they're not touching other people. I was so mad.
Yep.
Yeah, he like screamed at me. And then his wife was like lettuce and tomato. And I put lettuce and tomato on there. And he screamed. She said lettuce, not tomato. And she was like, I said lettuce and tomato. And he was like, now you got me cornered, made me look like a bad guy. I know.
Okay. Let's use the function x squared plus 2x. Picking that up. Let's do negative x squared plus 3x, and we'll find the area between 1 and 2. So what we've got here is a parabola. It should look like this. It should go 1, 2, 3. We want to find the area between 1 and 2. And we'll let the number of rectangles be infinity rectangles. So if we go back and we use this guy right here, we can highlight it, copy it, and paste it. Okay, what are we going to do? We're going to let n go to infinity. What we're going to do before that is use all those summation of formulas to bring it down to a place applicable. Okay, so here's f of x. So we're going to plug in a plus b minus a over n times I into x. Okay? So we're gonna let the limit as n goes to infinity, take an infinite, or a sum of an infinite number of rectangles from 1 to the nth one, to infinity ds1. It's gonna go from a to b, from 1 to 2. So b minus a, or delta x, b minus a over n will be 2 minus 1 over n will be 1 over n. Okay, I'm going to finish up this example during the first few bits of. All right, so like I said, I was going to finish up this example during lunch, so here I am. Let's see, so we're going to fill in the height and the width, right? So we just found delta x, that's the width of one rectangle, right? B minus a over n. So 2 minus 1, b minus a over n. We don't know what n is, we're going to let n get very big. So there's the width, 1 over n. 1 over n is also the width of the rectangle that we're going to move over 1, 2, 3, 4, 5 times whatever for the whatever rectangle that we're on. All right, sorry for that interruption. All right, so for the height portion of these rectangles, we would start at 1, and we would move over 1 width of a rectangle, 2 widths of a rectangle, 3 widths of a rectangle. For n is, or for I is 1, I is 2, I is 3, right? So what we're going to plug into each of these x's is we're going to start at 1, and then we're going to go over a width of 1 over n, right? Really skinny width if n is really big. If we had 100 rectangles, we move over 1/100th times I, whichever rectangle we're on. So if we're on the first rectangle, we move over 1/100th. If we were on the second rectangle, we would move over 2/100ths, and then 3 and 4 and 5 and so on. So we're going to plug this guy right here into x and this x, and that will give us the height for each individual rectangle if we were going to do this one by one. So negative x, which is 1 plus, let's say, I over n squared plus 3 times, I'm going to move this over in that room here, times 1 plus I over n. Now remember, I'm putting parentheses around this because this entire thing is the height of the rectangle, and this is the base of the rectangle, or the width of the rectangle. So we need the whole height times the width. Right, so now we're going to apply these summation formulas and clean it up so that we can apply the summation formulas, and then at the very end we can let n go to infinity. All right, so we just carry this through. For one thing, n is just the number of rectangles. It does not change. So it is a constant multiple that we can bring out in front here. We can also multiply it through if we wanted to. This is just what I tend to do. Okay. Then inside here, we need to square this parentheses, because what we're trying to do is get it to the point where we have summation of I squared, of I to the third if necessary. So we need to multiply this all out, right? So that's 1 plus I over n times 1 plus I over n. So that's going to be 1. We're going to separate these out too. It's going to be 1 plus 2i over n, because if we were to distribute these together, we get 2i over n plus I squared over n squared. Now keep in mind, this I is not the imaginary number I. I know that could be confusing, but this is not -1. This is not the square root of -1. This is not I, the imaginary number. Okay. So now remember also that we could, right now we have this 1 over n out here. We can split apart this as its own sum and then this as another sum. So plus this other sum, 3 times 1 plus I over n. Okay, so we took out that constant multiple of 1 over n. And we have parentheses around this whole thing because we also split apart this sum into 2 sums. Okay.
And now we have three different sums that will split into three different sums. Okay, so we have a, let's call it, we'll distribute the negative and call it -1. Yeah, we'll do that. -1, -2i over n, and -i squared over n squared. So we're going to have first this sum equals 1 to n of -1 minus I equals 1 to n of 2i over n minus, these are minuses because we have minuses in front. We could also put this minus out in front here, right? Minus sum from I equals 1 to n of I squared over n squared plus, okay, let's deal with this here. Let's pull out this constant multiple of 3. 3 times equals 1 to n of 1 plus I over n. Okay, so we can start to use summation formulas here on this one. Really what we're doing is we're going to put in a 1 and a 2 and a 3 and a 4 and 4 all the way to n, but all of those are just going to be 1s. None of that is going to be different. So we're just going to add up n 1s, so that's going to be 1 times n. So that part is just going to be n. Negative n. If you look at the summation for the summation rule for constants, you'll find that. Okay. Minus. Now we'll take this constant multiple of 2 over n. Remember, n is just the number of rectangles. That doesn't change, so we can pull that out as a constant multiple. 2 over n times, and we'll rewrite the sum. That's just going to be I is left there. We can pull out the 1 over n squared here. So 1 over n squared. We got I squared there plus 3 times, and we can split apart these two sums, so we have sum from I equals 1 to n of 1 plus sum I equals 1 to n of I over n. Right. And in this step I'm just going to, real quick, take that out. I'm going to take that constant multiple out of 1 over n. I'm just left with I there. Make sure to keep all your parentheses straight. Remember, we pulled out this 1 over n at the very beginning, and then we split apart these two sums. Okay, so this 1 over n is still way out in the very outside of these parentheses. And then, like for this one, we pulled out a constant multiple of 3 and then split apart these two sums, so that we still have this 3 times all this stuff. So just keep those things in mind. We used a formula here. There's a formula for this one. It's n times n plus 1 over 2. So this is 2 over n times n plus 1 over 2 minus this one here. This is 1 over n squared times the summation formula for this one is n times n plus 1 times 2n plus 1 over 6. I'm just going to double check. Yeah, that's correct. 3 times this guy right here, this is just going to be n again. We're just adding up n 1s, so that's just going to be n. So 1 plus 1 plus 1 plus 1, n times, it's going to be n. Plus 1 over n times the formula for this is n times n plus 1 over 2. Okay. Give ourselves a little more room. So again, as n goes to infinity, what we're going to wind up doing is like we have with rational exponents or rational functions, where we compare the degree of the numerator, denominator, and all that kind of stuff, and end behavior. If that rings a bell, that's what we're going to wind up doing here. But first, we have to put everything together here. Then we got to distribute the 3 into here, the 1 over n into here, the 1 over n into this whole thing, and so on. So we'll just plug away there. Negative n minus, well, this n and this n can cancel each other out. This 2 and this 2 can cancel each other out. So we can just do n plus 1. That's nice. Minus, okay, this n and this n can cancel each other out, so that's nice. So we get n plus 1 times 2n plus 1 over 6 plus, okay, we'll just leave the 3 out here for a second. N can cancel with n, we get n plus 1 over 2. Here, let's see, we got negative 2n plus 1 minus, let's say 2n squared plus 3n plus 1, just multiplying these together, or 6 plus 3n plus 3 over 2, just distributing that 3 to everything there. And now we've kind of dealt with parentheses in here, we can distribute this 1 over n. And if you want to get like a common denominator and put all these together, you can do that. But in the end, when we let n go to infinity, you can see that that won't be necessary. Right. So let's distribute this 1 over n. So we get negative 2n over n plus 1 over n minus 2n squared plus 3n squared plus 1. Let's see. All right, as will happen with these, I noticed that when I moved from this step to this step, I had 1 over n squared here, and then I used the summation formula, but I forgot n squared here. So only one of these got canceled out, and we're still left with an n. Just one factor of an n here, and it can't cancel out with one of these factors of n, so we should have a 6n down here. 6n. So all this is over 6n plus 3n over n, when you distribute this 1 over n in there, plus 3n plus 3 over 2n. Okay, so now we're at the stage where we can say what happens as n goes to infinity. So as this n goes to infinity, we can even just cancel these n's, and we see that we're going to wind up with a negative 2. This one, as n goes to infinity, n is going to become very large. 1 divided by a very large number. That limit as n goes to infinity for this term would be 0, so that's nothing. And let's see. Okay, and then what I should have here is we distribute the 1 over n to here, we should get 6 over n squared, or 6n squared. So we remember that if the degrees are the same, then as n goes to infinity, we approach the limit of, or we approach the ratio of these two guys here, these leading coefficients. So we have a minus 1/3, if we simplify that. This one will have, this will be a 3. This one will have, this will approach 3/2. Okay, we add those all together, and we're good to go. So we have a common denominator of 6, so this is 12/6 minus 2/6 and plus 9/6, or plus 18/6, my mistake, 18/6 plus 9/6. Okay, so negative 12/6 minus 2/6, negative 14/6 plus 18/6 is 4/6, plus 9/6 is 13/6. Okay. I know that can be difficult to follow. I have other examples up that you can check out on the other playlist. It's just normal sample problem videos, so check that out as well. There's also probably some in pre-calc that you can look for there, summation notation formulas. And of course we'll go over this in class as well. So thanks for watching.